Hello again. Okay, section B, extended questions. Okay, so we're on to question 16. Ions and compounds containing hydrogen. So you're told that the AlH4 minus ion, it's got to be covalently bonded. Don't forget, one of them is going to be a dative bond, so you need to show the same symbol for those two electrons. And square brackets and charges. When you're drawing an ion, you should always do that, although I do think the mark scheme says that they wouldn't penalise you for not putting the square brackets, but you don't know that that's going to be the case. Try and remember to always put in the square brackets and the charge. Very important to put the charge, okay? And then you're asked about shapes here. I mean, obviously this is AS stuff, you know, so you had to make sure that you had revised your AS stuff. NH4 plus, you've got 4 bonding pairs surrounding nitrogen, so it's going to be a tetrahedral shape. Learn those bond angles. NH2 minus, so you've got 2 lone pairs and 2 bonding pairs this time, a bit like water, so non-linear or bent. And the bond angle, don't forget, is reduced by 2.5 degrees for each lone pair. So the bond angle 104.5. Straightforward enough. Okay. So you're given some boiling points here, and you're asked to explain why the boiling point of phosphorus hydride is lower than the boiling point of ammonia. And if you don't recognise, first of all, that the question is about intermolecular forces, and secondly, that NH3 has hydrogen bonding. Yeah. So you need to show that you understand that hydrogen bonding is stronger than the intermolecular force between pH3. So you've got your marks for that. And then again, you're looking at different intermolecular force. So this question is testing your knowledge of all of them, really. Here we're talking about London forces, why the boiling point is lower than the boiling point of ASH3. It's a bigger molecule, it's got more electrons, and therefore has stronger London forces. So again, you need to recognise that the bigger the molecule, the more electrons it has, and that will lead to stronger London forces. Again, it's AS material. Okay, looking at group 2 and group 17 or group 7. Write an equation for a neutralisation. Pretty straightforward, you should be able to do that. Acid plus alkali, salt plus water. And then you're asked to explain why the reactivity of group 2 elements increases down the group. So you need to think about the factors that affect reactivity. Again, S is AS stuff, an increase in the radius, which increases the shielding, which reduces the nuclear attraction, and therefore less energy required to remove outer electrons. So obviously they're going to react more easily. Okay. Okay, so definition of disproportionation, you know, you have to know it. It's obviously the fact that an element is both oxidized and reduced in the same reaction. Okay, and then you're asked about use oxidation numbers to show that disproportion has taken place. Yeah, so you're given the equation up here. You should know these, be able to work out these oxidation states. We've got 3 times minus 2. We've got plus 1. So our chlorine in this case is plus 5. So whatever happens, it's going to be plus 5 to something, isn't it? So then you have to work out the oxidation state of chlorine in the 2 products. So in KCl it's minus 1, and in KClO4 it's plus 7. So you're going from plus 5 to minus 1, which means you're gaining electrons, and then you go from plus 5 to plus 7, which means you're losing electrons. So oil rig, reduced and oxidized, yeah. Systematic name for KClO4, because it's plus 7, this is where you use your Roman numerals, so you have to recognise the ClO4 is chlorate, so potassium chlorate 7, which is indicating that chlorine is in the oxidation state of plus 7. That's what the Roman numerals tell you. Okay, write an equation here, including state symbols, very important. If you forgot those, then you couldn't get the mark. And then it says state and explain. So state the entropy change and then explain why you've stated what you have. So you have to write the equation and make sure that you've got the barium sulfate here is a solid, yeah, which means that this reaction has moved to a lower entropy. So we've got two solutions here, and we're forming a solid plus solution here. That's going to lead to less disorder. And then you're asked to write this equation, and I'm not sure that anybody got this right. And this is the importance, really, of knowing your definitions of enthalpy changes, and I've written it down here. Enthalpy change of atomization, when 1 mole of gaseous atoms is formed from its element in its defined physical state under standard conditions. So you can't have I2 here, yeah, because we're forming a mole of gaseous atoms, so we need half I2. But some of you did recognise that you're going from a solid to a gas, so entropy is increasing. Okay, but that is important about these definitions of enthalpy change. Right, question 18 about delta G. Okay, and you're given the equation there and a graph with some letters, and then you're asked to discuss basically those different points on this graph. So your starting point here really is this is a straight line graph, so you should be able to link it to your y equals mx plus c, straight line general term, and then rearrange the equation, yeah, so that it fits this. Y is delta G, yeah, x is temperature, the gradient is minus delta S, and C is delta H. Okay, so we've got minus delta S is gradient, T is X or Q in this case, yeah, and that will be the temperature at which the reaction becomes feasible. Delta H will be C or P, so the y-intercept, yeah. Now that's going back to your maths, really, recognising that from your maths. Okay, part B, we're given an equation, an equilibrium here, and you're given delta H and S, and don't forget the units. You know, you're going to have to change some units probably if you're working with these two values. Okay, so again, this is a definition, heterogeneous equilibrium. You're asked to write KP expression. Now, a lot of you didn't recognise that you've got three solids here and they don't go into a KP expression because this is only refers to gases. Okay. Alright, okay. Show that the forward reaction is not feasible at 25 degrees C and calculate the minimum temperature for the forward reaction to be feasible. Yeah. So we can use our equation to, but obviously we need to convert our 25 degrees C to K and put that into the equation. Now we can then state, obviously, once you've done this calculation and you've got it right, it's not going to be feasible because delta G is greater than 0. So then to work out the minimum temperature that it would be feasible, yeah, we use this equation, delta H over delta S, and this comes from this a rearrangement, basically, that when delta G is 0, then T delta S is equal to delta H. And once you rearrange that, you can get the minimum temperature, which is very straightforward. So these calculations are not difficult calculations, but your problem arises if you're not sure how you're going to use that equation, delta G equals delta H minus T delta S. Okay. Right, okay, now we're given another equilibrium where we're forming iron, yeah, and you're given some enthalpy change of formation data. So, and asked to calculate the enthalpy change of formation for carbon monoxide. Carbon monoxide in the equation here is on the left-hand side, yeah. So you're forming carbon monoxide, so you want to swap that around, which means you have to change the sign of your delta H. Okay, so I've just rewritten the equation where I'm forming carbon monoxide because that's what you've been asked for. Yeah, calculate the enthalpy change of formation for carbon monoxide. And then once you've written that, I mean, you put your elements at the bottom here, and then you put your arrows in to show the routes. So your delta H is obviously the enthalpy change of reaction. That goes on that arrow. Recognize your two routes. Because this is formation, these elements are forming these substances. So the arrows are going up. So you've got this route and this route. As long as you put the numbers on the right side, then you can write your equation properly. Don't forget you've got 4 carbon monoxide, so that's 4x. That's your unknown. Yeah. And then this data here, 4 times CO2. No enthalpy change of formation of iron because we don't form elements. And that's it. And then it's, you know, pretty straightforward calculation. Just get X on its own. Okay. Okay, so question 19. This is rate question, obviously. We've got a concentration time graph that's been drawn. And then you're asked to determine the total volume of oxygen, first of all, that the student should be able to collect if the reaction went to completion. So that's pretty straightforward, working out the total volume of oxygen. And then you're told or asked to suggest apparatus that you could use, indicating clearly the scale of working, which means that you have to show that you understand that you need to use a measuring cylinder that is bigger than 690 cubic centimetres. Okay, so calculation, work out your moles from the data that you're given, then look at the equation up here, 2:1 ratio, hydrogen peroxide to oxygen. So you divide your number of moles by 2 and then convert to volume. Again, without remembering all your mole equations, you could get a bit stuck here. Okay, but the most important thing was that you had to say 1 cubic decimetre or 1,000 cubic centimetre measuring cylinder. And then a different method would be, obviously, because you're producing a gas, you could actually measure mass loss over time. And then we come to one of the questions that's got the asterisk or the star against it, which means the marking system is slightly different. You're asked for overall a level. Is it a level 3 answer, level 2, or level 1 answer? So and it does say what you have to calculate: initial rate, order, and the rate constant, and you must show full working on the graph and on the lines below. So, you know, be methodical when you answer these questions. Right, initial rate. Okay, how are we going to do that? You're going to take a tangent, so make it clear what you're doing. Yeah, that t equals 0. So if you go back here now, I've, you know, made it really clear my tangent. I've used a pen. I wouldn't normally use a pen on a graph, but in this instance I think it's okay to make it clear to an examiner exactly what you've done. Okay, so you work out your initial rate, what value on the y-axis over the value of the x-axis, and it turns out to be 1.6 times 10 to the minus 3. Then you're going to work out how you're going to work out the order, basically. Because it's a concentration time graph, you can look at the half-lives. Yeah, so you're starting with 2.3, and some of you tried to do half-life but started at 2.5, but the graph actually is 2.3. So you go for half of that. You can't see it too clearly actually. I thought I'd done it here, but it's actually here. Yeah, half of it. Come down. Work out your half-life is 900 seconds. And then obviously you halve that value. And again, that works out to be 900 seconds. So that tells you that this is first order because the half-life is constant. So make it clear that you understand that and scribble down the rate equation. And then the last part, you're asked to calculate the rate constant. Yeah. So you've got the rate, which you've worked out. You've got your concentration of H2O2, and off you go. Okay, so you know, if you want to get 6 marks, you just really need to be methodical and point to what you're doing, as I've done here. Right, question 20, equilibria. Again, this is, you know, give a methodical answer. You're given an equation, you're given an enthalpy change value, you're asked to explain, which means to make clear why, using Le Chatelier's principle, what the conditions of pressure and temperature would be for maximum yield of hydrogen. So you need to explain each one. So take each one in turn. Look at pressure. You know, we've got more moles on this side, we've got 4 moles. On this side, we've only got 2. So if we increase the pressure, it's going to push the equilibrium to the left, which is not going to help us because we want the maximum yield of hydrogen. Yeah. So you need to say that. So the low pressure would give more moles of gas on the right hand side because blah blah blah. And then the same for the temperature. So it's an endothermic reaction, which is good for us. So if we increase the temperature, we can increase our yield because the equilibrium will shift to the right, absorbing the energy, yeah, going in the endothermic direction. Okay, and then just finish off by summarizing, therefore, the conditions for this reaction to produce a maximum yield of low pressure and high temperature. But you've got to explain them to get the 4 marks. Okay, part B, another equilibrium we're given. Told that they're mixed together, the sulfur dioxide and the oxygen. The gases are then compressed to this volume, and the mixture is heated to constant temperature and allowed to reach equilibrium. And you're told that the equilibrium mixture contains this many moles of SO2 and this many moles of O2. And obviously that's moles, not concentration. So you need to bear that in mind. And that should, as soon as you read that, you should be thinking, right, okay, I'm going to have to do some kind of conversion here. So you're asked to write the expression for Kc, which is straightforward, and you're asked to give the units. And of course, don't forget these square brackets mean concentration, which is why you will not be able to use these values as they are in the question. So the amount in moles of SO3 in the mixture. So we're looking for this amount of moles. We're given the moles of SO2 and O2 that we start with. Okay, so calculate the concentrations first. Need to be in cubic decimeters. So at the moment they're in 400 cubic centimeters. So if you multiply those values by 2.5, it gives you the values in cubic decimeters. Just 4 times 2.5 takes us up to 10 effectively. Yeah. Okay, so we've got our concentrations now, and then it's just a matter of rearranging. So we need it for SO3, and because SO3 is squared in the expression, the square root of the other side of the equation will give us the concentration of SO3. So after that, it's just a matter of putting numbers in. Don't forget that your SO2 is also squared, so the value for SO2 needs to be squared. And then finally, because this is in moles per dm cubed, but in our reaction vessel we only had 400 cubic centimeters, don't forget you need to divide by 2.5 to come back to the equilibrium mixture itself in our reaction vessel. Okay. Right, number 21. So this is a weak acid question, pH and etc. So you're asked to calculate the concentration of ethanoic acid in the solution and to give your answer to 3 significant figures, which a number of you didn't do, and then of course you lose a mark for that. If you've done the calculation properly, it's really annoying. Okay, so how are we going to do this? We're given that a value up here that the pH was measured to be 2.440, which gives us a clue if we need to work out the concentration of H+. Yeah, so that we'll do that by 10 to the minus whatever the pH is. We've got our expression for Ka here. Don't forget that our H+ and our conjugate base, they should be the same concentration, so we just shorten it by squaring H+ here. Once we know H+, from this calculation, we put that in, rearrange that for CH3ClOH, because that's what we're looking for, the concentration of ethanoic. We're given Ka, there you go, put the numbers in, and there's your answer. This one is a little bit more complicated than usual, maybe, because you're given 2 Ka values, and obviously you need to compare the Ka values to recognise which one will act as the acid and which one will act as the base. Okay, so this is the stronger acid, so it's going to be this is the acid, this is the conjugate base. This is acid number 2, obviously, which is going to release the hydrogen ions, got one spare, and this is acting as a base. Okay, but it is a little bit harder than probably any examples we've done, in the sense that you needed to work out from your Ka values. Okay. Part C. So this is about buffers. You're told it's got that these wants to prepare a buffer solution with a pH of 4.5, and this is how he's going to do it. He or she is going to do it. So you're going to use this information to work out whether or not the pH would be 4.5. Okay, so you need to write your Ka expression, but then you need to rearrange for H+. Okay, so we can work out how many moles we've got of the salt, because we're given a mass. Yeah, and then we can work out concentration. Which, because we've got moles, we can get concentration, we've got the volume, 250 cubic centimetres, and then obviously once we've rearranged, so we've got Ka, we've got this value now, we've got the salt, the conjugate base, we've got the acid concentration, which is given to us in the question. So it's just a matter of putting the numbers in. So there's your concentration of H+, which will, if we take the pH of the minus log, if we take the minus log, we'll get the pH, which comes out to be 4.5, which means, and you must make that final statement to say that the student's method will produce the required pH. So when it's a buffer question, don't forget you are going to need to use this buffer equation, which kind of flips the conjugate base here and the acid over, you know, from the original Ka expression. And that's because, don't forget, in a normal, if it's just an acid, these two will be the same, so we can square them. But in a buffer, that's not going to be the case, because we've added the salt, so that we've got lots more conjugate base. Okay, the last question. It's saying that originally, in the original question, it said that the student ignored the volume and assumed the volume didn't change, but it's saying here that the volume did increase slightly, and will that change the pH? But there's no reason why the pH would change here, because your ratio of your acid to your conjugate base is not going to change. The ratio will stay the same, and that's basically what your pH is measuring. Right, nearly there. question 22. So this is an electrode potential question. First question is asking you to look at system 1 and 3, so the zinc and the iron. Okay, draw a label diagram to show how the cell could be set up. Don't forget, you must show your salt bridge in the solution, you must show your electrodes in the solution, and you must include a voltmeter because that's how we measure the cell potential. Yeah. Okay, and then we've got our electrode of zinc and a solution of Zn2+, and I've put the concentration in here because that would be the expected concentration under standard conditions. Over here though, obviously we've got Fe2+ and Fe3+, so they're both aqueous ions. Both of them would be 1 mole per dm cubed, but our electrode would be platinum. Okay, and the standard conditions, you should know them, you should get easy 4 marks there. Predict the standard cell potential, that's positive minus negative, you know. So there you go, positive minus 1.53. The strongest reducing agent, look at the table, the strongest reducing agent will be the one that is most negative, and the strongest oxidizing agent will be the one that's most positive. And then the more difficult bit of the question, I suppose, is predicting the feasibility. So this time you're looking at systems 2 and 4. Yeah, and I think some of you didn't recognise that. I'm just asked to construct an overall equation for this predicted reaction. So you need to look at the 2 equations in the table, yeah, 2 and 4, okay, and look at these values, which one is more positive, which one is more negative. So don't forget, the more negative equation you're going to swap around. Yeah, you have to change it around. And then once you've done that, so I've swapped it around here, I've got SO3 2- first, then you need to balance the electrons. So we've got 5 electrons here, we've got 2 electrons here, so we multiply this equation by 5 and this one by 2. We're going to end up with 10 electrons for both half equation, and that means we can cancel them. So, and there will also maybe the opportunity to cancel some other things as well. So in this case we've got 5 waters on this side and 8 on this side, so we can get rid of those 5 and we're left with 3. And with our H+, we've got 10 here and 16 here. So again we can cancel that 10 and we're just left with 6. And then your final equation, nice and tidy, it's just got everything that needs to be there. You did get a mark, I believe, if you forgot to cancel things, but you didn't get the 2 marks. So try and remember to do that. Okay, so and then this is the last question. This is on the transition metals. So you need to know these reactions, you know, what colour change, because colour change is kind of a hint to you as to what's going on. So we're starting with our hexahydrated copper ion. We add hydrochloric acid to it, and then we get a ligand substitution. The water's substituted by the chloride, and you notice it's taken on a different shape as well. So it's worth, you know, thinking about these things. If we add ammonia, our first part of the reaction is to form copper hydroxide, and then if you carry on adding ammonia, you get that deep blue lovely complex with 4 ammonia ligands and 2 water ligands. Okay, and this is a straightforward redox reaction. If you add potassium iodide to this, you get copper iodide, iodine. Okay, and then the names of the types of reactions. Okay, and then we've come back to our the last part of the exam, the last question, and it's a starred question, given some information, and it's complicated in the sense that you're asked to come up with a formula 4 different substances and show the 3D structures for the isomers. So you really need to be methodical when you answer these questions. You know, read through all the information. Why have they told you this? Why have they given you that? So my first thought was the most obvious thing to work out is complex B, because we're given these percentage by mass, yeah? So it's easy to work out an empirical formula from that, isn't it? So I did complex B first, yeah, and we've got our formula, so there's 1 mark. Then I looked for complex A, so you need to recognise complex A obviously is the hydrated form where you're going to get the information. It's going to come from up here, yeah, where you're heating complex A and you're left with complex B, so you can work out how much water basically has come off our hydrated complex, yeah, because this is the anhydrous formula, so we can work out how much water, yeah, and the ratio is 1 to 2, because we've got this many moles of complex A and this many moles of water. So your formula for your hydrated complex will be dot 2H2O. Remember that, water crystallization. Then you're told that the cation is 6 coordinate, and it's got 3 molecules of the bidentate ligand D and exists as optical isomers. And cation C comprises of nickel, carbon, nitrogen, hydrogen only. So you're also told that. So if you know it's only got nickel, carbon, nitrogen and hydrogen in it, obviously it's going to come from here, yeah. And hopefully, I don't know, I mean, you know, you have to make that jump here. I mean, you know, there are certain ligands that you need to know in the formula, so it's only a couple of them. 1,2-diaminoethane, yeah. And this is what it looks like, and this matches very nicely with this formula, yeah, because there's 3 of them, don't forget, we've got a 6 coordinate. We know that our nickel is in the middle, yeah, and you've got to draw the optical isomers for them. So if you look at these diagrams, you can see that these ligands have kind of all just moved round one, yeah. So here you're going from this bond, the one that's going back into the paper, to the one in the plane of the paper. Here you're going from the one in the plane of the paper to the one going back on the right hand side. So each of these bidentate ligands is connected in a slightly different order. That's just practice really, because they're pretty much, you know, the same. If they're 6 coordinate, that's what the optical isomers are going to look like. So as long as you can draw them, there's nothing to stop you getting all the marks. And okay, and that's 6 mark questions. A lot of work there actually to get your 6 marks. So you do have to be working quite quickly and be quite familiar with them. But overall, if you break it down, it's actually not that difficult. But I think it's off-putting when you read all this and you think, I don't know where to start. But like I said, you need to look for the most obvious thing that you can work out. And to me, this stands out really clearly. And then at least you feel like you're on your way with the question. And then, you know, once you start it, quite often it's not that difficult to carry on. Okay, that's it. What a long feedback, because it's a long paper, isn't it? Okay. Speak to you soon. Bye.